All right, physics class, it looks like we're finally back to recording again. Hopefully this is picking up my voice and everything's working. We'll see in just a minute or two. But you'll see that my picture's not on there. I don't know why, but that's okay. These are notes today on the energy model. And when we talk about the energy model, what we're talking about is the fact that energy within a system is always conserved. And that you have a sheet that looks like this that you'll see. And we'll come back to this in just a little later. But the key ideas are that energy is conserved, that within a given closed system, energy is not going to leave or enter that system, or if it does, that you're going to account for that. So let's take some notes here. So the first thing that probably is important to remember is, or to know, is the law of conservation of energy. The law of conservation of energy says that energy in one location within a system is going to be the same as the energy in another location, so that energy is conserved. It doesn't disappear. It can go somewhere. It can be stored or it can be transferred, but it doesn't ever just disappear. So let's look at an example of that. So here we have an example of someone coming down a slide. As they come down the slide, they start here. This is the steps going up, and here they are at the top of the slide. And as they come down the slide, their energy, the form of energy, is changed. So, for example, the sum of the energy at the top of the slide would always equal the sum of the energy at the bottom of the slide. That's what this is the sum of, this symbol. So this sum. However, though it stays the same, it does change or is transferred. So, in other words, if you added the kinetic energy and the potential energy at the top of the slide, and you added the potential and kinetic energy at the bottom of the slide, you would see that those two are equal. So what do we mean by potential and kinetic energy? It's probably been a while since you were thought about this. It's been middle school probably. So kinetic energy is the energy due to motion, where potential energy is the energy due to position, or to some device like a spring or elasticity. So if you're on a slide, at the top, when you're stopped at the top of the slide, you have maximum amount of potential energy. You have the potential to, due to gravity, to drop. When you're at the middle of the slide, and you've picked up some speed, you have some potential energy and some kinetic energy right here. And as you come on down farther, when you're here at the bottom of the slide, your potential energy is gone and you have all kinetic energy. So the amount of energy stays the same, but you've transferred from all potential energy to all kinetic energy. So let's look then at another example. This is the roller coaster. Typical example. You're going to be making a roller coaster in class for a lab. But let's look at the roller coaster. Similar kind of thing. So here you are. You have the car at position A at the top of this roller coaster. B is when the car is at the middle coming down the slope. And then C is when it's reached its the lowest point that it'll reach. And if you look at that, you can see that up here at the top of the slope, the potential energy is at the maximum. It would already have speed, so in this case it also would have some kinetic energy. But the potential energy at the top of that hill is probably maximum. The kinetic energy, there's a little bit of kinetic energy. But as you come up to the top of that slope, you really slow down. And you don't stop, but you've slowed down significantly. So you don't have a lot of kinetic energy right there. But as you come down this slope, right, your kinetic energy would increase, and your potential energy would decrease as you came down. And as you get to the lowest spot, your potential energy would drop to 0, and your kinetic energy would be maximum. So one of the ways that we represent energy is we represent them in energy pie charts. And a pie chart is just like a pie graph, right? Where the whole circle is 100%, right? If we think of the circle of the graph, it's 100%. If you had half and half, right? You'd have 50% and 50%, or you could have 3/4, which would be you know, something like this, right? 75 and 25. But it's just a pie chart is really what it is. So if you can imagine a falling object. So here's an object. It has, this represents a gravitational energy, and this represents kinetic energy. Well, gravitational energy is also potential energy. So at the top, as this object is falling, it's released here at A, and it's going faster and it's going faster. You know all about this already. And so at the very top, Eg, which is the potential energy, but it's energy due to gravity, is at 100%. So your pie chart would look something like this. It'd all be shaded green. When you get about, you know, part way down, you might have, oh, this isn't a very good pie, but you might have 75% of that potential of gravity, so gravitational energy, and maybe you only have, you know, sped up a little bit, so your Ek is about 25%, your kinetic energy. And then as you get farther along, and you finally get to the bottom of this whole thing, right, your potential energy is completely gone, and all you have left is then this kinetic energy due to speed, which of course is going to be why you splat when you hit the ground. So you've had a transformation from this potential energy called Eg to kinetic energy over that path. We also often look at little Energizer bunny problems, and if you can imagine, this is a diagram like we had way back in constant motion, right, where we would show the vector which represented, you know, how fast you were going. So if you look at this, when you first wind up one of these little Energizer bunnies, this is a little wind toy that has elastic energy, it's going to go really fast, right? But as it winds down, it goes slower, and then it stops. So here, initially, we have a lot of kinetic energy. So you might have 100% kinetic energy here in this situation. However, when you got to this situation, you would have a little bit of kinetic energy, and you'd have a fair amount of thermal energy, which is heat. And then when you finally stopped, you would have no kinetic energy left because you're stopped, but you would have 100% thermal energy. So as you traveled along, this energy was transformed from kinetic energy to thermal energy. So if we look a little bit more closely at this energy model sheet that you have in your packet, and you'll read through this. This section right here we'll go over later, but what's happening here is that we're looking at the change from energy here from gravitational energy to kinetic energy and gravitational energy and some dissipated energy. So this is Buffy is throwing a water balloon at Biff's head, and you have lots of kinetic or energy or potential energy due to gravity here. You have some Ek and some Eg, and then some dissipated energy. These we'll do not at first. This is the second thing we're going to do. So just look that over. But then look more carefully down here at your equations, which we'll be using a little bit later as well. But gravitational energy is the mass times gravity times the height. So this is where we start looking. When we look at force, we look at matter, mass, and gravity, right? Or mass and acceleration of gravity. But here we look at the height, because the higher you are from the ground or from the base, the more energy you would have. Elastic energy, which is the energy like in an Energizer bunny, is this equation. EL equals 1/2 K. This is a constant that has to do with the kind of material we're talking about. And this is the square of the distance. And then our energy for kinetic energy is 1/2 mv squared. So 1/2 times the mass times the velocity squared. So we're looking at some similar things that we've looked at before. So this also gives you some other information. It talks about working, heating, electromagnetic radiation, which are kinds of energy transfer. It talks about also some useful numbers. So those are all things that we'll be going over. So you should read this before you come to class and be ready to discuss any of these things. But we will come back to this kind of representation of energy. We'll be starting off with the energy pie charts that we just talked about. So that's it for now. There's no exit problem today because there just isn't. We'll be talking about this in class.